Hello and welcome to our senior design presentation. We are the Resistor Rangers, and today we're excited to share our project. To start, let's introduce our team. I'm Stephen Evans, and I will be responsible for testing and validation.
I'm Mitchell Woolhoff, and I'm covering energy storage.
I'm Doug Harrison. I'll be responsible for integration and design verification.
I am Eduardo Conchas, and I'll be in charge of protection and automation.
I am Bianca Lemon, and I will be working on the microgrid controller.
Power outages can be detrimental to research efforts, so we chose a project to create an uninterrupted power system for a new research center at ASU that will help students, faculty, and other researchers. The building already has a backup generator and a solar array, but those alone can't ensure continuous operation. Therefore, we will design a battery bank for power storage and a microgrid that will incorporate system protection, island detection, load shedding, and synchronization with the utility feed for seamless automation.
It's easy to see how microgrid systems help the general public. In some situations, continuous power saves lives, such as in hospitals. In other cases, such as data processing, interrupted power can cause the loss of essential data. According to recent market surveys, over 50% of microgrid systems are utilized in healthcare, education, and national defense alone.
Let's take a look at the architecture of a microgrid system. A microgrid integrates multiple small power sources, such as solar panels, wind turbines, or small generators, that are usually attached to a centralized national power grid, but is able to function independently without external input. The power produced by these sources will be fed to inverters, which will synchronize and unify the generated power into a single source. The power that is not immediately consumed can either be fed back to the grid and sold, or stored in battery banks or other methods of storage. Finally, at the heart of any microgrid will be the sensors, communications, and control systems that monitor the flow of power and ensure seamless transitions between and among the various power sources. Together, these components make a microgrid a flexible and reliable power solution.
What are our goals for success? The key goals for success include zero downtime, ensuring that the controller prioritizes critical loads, a smooth transition between power sources, ensuring the power supply meets the load requirement and not damaging sensitive lab equipment, and ensuring integration with the existing lab infrastructure is effectively and efficiently implemented.
One major technical challenge is designing the controller for the microgrid. It needs to prioritize critical loads and balance power from solar, battery storage, and a backup generator. A seamless transition between these sources is essential, especially for lab equipment sensitive to voltage or frequency changes. We also need to ensure the energy storage can meet power demands during low solar generation and maintain power quality to prevent damage to critical systems. Today, we discussed the need for an uninterrupted power system at ASU research centers, the architecture of microgrids, and the key challenges ahead. Our next steps focus on overcoming these challenges, managing complex loads, balancing power sources, and designing a controller for seamless transitions. Addressing these will ensure a resilient and sustainable power solution for continuous lab operations.
We thank you for your attention and for viewing this presentation.